Welcome, everyone. So we've turned the corner on a new sort of module, a final module of this course, where we are going over materials from papers related to Sheaves, and with two particular papers on the docket. One of them by colleagues at University of Florida, James Fairbanks's group, the Gaddis group, and the second by Michael Robinson. And for today, I had requested to go through the first part of this paper that's entitled Towards Unified Theory of Time-Varying Data. And this paper, I will note, formed a central motivation for exploring the topic of sheaves within this course. It's not the only motivation. I had other inklings of the value of this, but this particular paper highlighted for me the potential for combining sheaves with categorical computing in the form of CATLAB. And that remains a topic of foremost interest. So I think all of you are familiar with the some broad elements of the paper. I will share my screen here. And we'll note that this paper was presented at the Applied Category Theory Conference in 2024 in Oxford, where I was present, and I had the pleasure of hearing the talk accompanying it. I will further note that James Fairbanks, and by extension his group, have been central collaborators, one of the two biggest collaborators, together with Evan Patterson, towards the creation of the algebraic Julia ecosystem. And this paper seeks in its approach to take it's aligned with that ecosystem in the sense that amongst other things, they are targeting categories that are CSAT categories, or equally pre-sheaves or co-pre-sheaves. And they do so in part because all those categories support pullbacks. All those categories, in fact, support topuses or topoi, these really nice places to do math that, amongst other properties, like having colimits, having exponential objects or internal HOMs, having an object that represents morphisms between any other two objects, having what's called a sub-object classifier to do logic within the topos, to do and or, etc. They also have limits, and they have pullbacks, and they do have push-outs, so colimits, all of which are relevant here. So this paper is an interesting one. They start out with desiderata, right? For what they say strategically would be desirable properties of any mature theory of temporal data. And as part of the paper, they critique, as it were, ad hoc theories of temporal structures, like temporal graphs. And one of their critiques, well, a broad critique along those lines, is those theories of temporal structures, like temporal graphs. Many different theories have been put forward for those, but many of those theories do not admit favorable properties formally. And they're inconsistent with each other, et cetera. So they seek to articulate in a rather ambitious way an approach for capturing temporal data using sheaves, but using C-sets and to secure from that a wide variety of benefits, right? So they have this ability to capture narratives, sort of temporal narratives that are either persistent narratives, as they call them, or cumulative narratives, where the first is associated with sheaves, the second with co-sheaves. They have this ability to articulate with mappings between instances of C-sets, sort of morphisms within these narratives from one snapshot to the next, that mean these snapshots are not solitudes. They have some relationship with each other. But they also have ways of converting cumulative narratives into persistent narratives and vice versa, using what are called adjunctions, which are extremely powerful and beautiful things. Systematically capturing the different worlds associated with persistent narratives and cumulative narratives, and recognizing there's so much structure that's kind of mirrors of each other, you can convert one to the other. They show how this can be done with integer intervals or with real intervals. They show how you can convert from a narrative, be it persistent or cumulative, with respect to one type of C-set data, to convert to narrative for a different type of C-set data by changing of base, as they call it. And they show how you can take properties of structures that are static, like recognizing a clique in a network, or recognizing a path in a network, or doing, identifying betweenness centrality in a network. And how you can, through the power of functors, lift that property into these narratives and apply it over time. And by extension, as I recall, they further show that some of those liftings accord with some approaches in the literature that have been used ad hoc in the past, and some do not accord with more limited past ad hoc approaches. Now, to do this, they make use of a Grothendieck topology, capturing what's called, in a rather a mouthful, subjoined semilattices. So these are lattices, they're preorders of inclusions of intervals where you have all meets. So you have all, take two intervals and finding an interval that includes both of them, from the minimum of the smaller one to the maximum of the larger one. Recognizing that's a bit handled. And using that form and recognizing at the lowest level with these mappings between snapshots, they can put in place this infrastructure. So the growth indie topology they're using is based on a category. Remember, growth indie topologies allow us to work on categories of where we have open sets and where we have morphisms involving that contribute to those open sets. We talked about it last time. They're using those allow us to do it with these categories with pullbacks for the most basic definition we talked about last time. And their category is one created by Spivak, Vasilikopoulou, Schultz, and I think maybe one other, involving intervals as objects. So each object is interval. Think maybe, for simplicity, think about an integer interval. And the morphisms are, again, a mouthful, orientation preserving isometries. So basically, they're not like compressing one thing down to another. It's not like interval 0 to 2 can get compressed into interval 0 to 1. It's just that some intervals fit as inclusions into other intervals, but you're not allowed to flip the order, right? You can't take an interval 1, 2 and turn it into an interval 2, 1. That's the orientation preserving. You don't get it doesn't do the twist, right? And with this category, they have a notion of coverage where the cover of an interval going from a start time to a finish time, save time 1 to times 7. You can have a cover for that. For example, if you have one interval from 1 to 3 and another interval from 3 to 7, that will sort of cover that, right? And importantly, this is a pre-order or post-set category. They use the term it's post-settle, which is kind of an adjectival form of saying it's a thin category. It's basically a post-set, a partially ordered set, a pre-order. So it looks something along these lines, right? Like we can have 0, 2 in the okay, so this should be in the interval from minus infinity to plus infinity. But 0, 0 and minus 1, 1 are both in the interval minus 2 to 1. And you could have, if I had more time with this, I would have shown interval 1, 2 would be in the interval 1 to 3. It would also be in the interval 0 to 1, or sorry, 0 to 2, etc. And importantly, when they say that they have subjoint semilattices, the join here for two intervals, say minus 1 to 2 and 0 to 2, is the minimum of right, the minimum of their starts going to the max of their finishes. So minus 1 to 2 and 0 to 3 would be minus 1 to 3. And in the paper, they don't really deal with meets. They're not dealing with meets. They're not dealing with these direct. They're not imposing that they're talking about joint semilattices. But yeah, it may be that meets are automatically present through pullbacks of that, but I'm not going to comment on it. Okay. So they have this category involving these. And maybe what I will do is, from this paper, if we go and we look at some of the nice, this is the extended abstract. They have an extended abstract, which is pretty substantive itself. Here it is. Here's the paper itself. Okay. Let's do it in this presentation mode. So I did want to talk about this side of things. So maybe what I'm going to do for this is break out the tablet. And I am going to, how do I escape from this mode? I need to, how do I escape back? Well, maybe I can just do this. Okay. Um, uh, okay. It's like it's a random background. Each time it picks a background and I don't know how to change it. Okay. Um, without the menus. Okay, well, that will do for our purposes. So what's really important to realize, and what I was confused about the first time I saw this paper, was that we're going to be dealing with these intervals. And then we're going to be dealing with data over the intervals, right? And I thought they might have a nice picture of the intervals here, but it looks like they don't. Maybe I will draw some things with the intervals. Do they have a nice interval picture in here where they show a nice mapping? I remember this from the presentation, but I'm not sure it's in the paper. Is there a nice picture of sort of a mapping between two things in here? Does anyone remember? I'm looking. I don't see it. Do you see it here? Uh, did you see any nice picture of a lattice being mapped into data? If not, I think I'll just draw it out. Okay. Um, so what it looks like is this. So down here at this lowest level, we have, no, put these in slightly more gracile font. So we're going to have things like time period 1 to 1, time period 2 to 2. These are going to provide the basis for snapshots when we map them into data with Sheaves. These are taking part in our topology. Okay, of sorts. Okay, now we're going to have an interval over this, which is going to go from 1 to 2. This is going to be a join of these two. And I think you'll recognize this lies within that, and this lies within that as an interval. And here we're going to have another interval, 2 to 3. This, and then we're going to have an interval 3 to 4. But we're not only going to have these things. I'm just drawing some. Right? We're also going to potentially have, for example, 2 to 4 as a result of these 2 to 4. Right? And we're going to have 1 to 3 here. Right? Now, you might ask, well, excuse me, am I doing something? Yes, that's right. That's right. And then there can be some interval up here, which So these are little hooks down at the bottom. All the arrows are inclusions and they go up to the top. Notice that these are not disjoint, but they do collectively fit in to this, right? We need those nice little hooks here. Mm-hmm. Mm-hmm. Okay. Now there's going to be a functor. So this involves some objects. So these are objects, right? These intervals, these are objects. And these are orientation, preserving isometries. We're not changing the metric. So this is mapping of temporal category into data. So then for a sheaf, we're going to have sheaf F. We're going to have a mapping from T, and what do I have to put? T for a sheaf into some data category, right? And these data categories are going to be of this general form. So we're going to have, these are actually C sets, okay? These are going to be C sets for them because the C sets are guaranteed to have, in this case, limits. And so this functor is going to be a limit preserving functor. Yeah. Okay, now you'll notice because of the op, we have this kind of reversal in the direction, right? But I think you're going to get the basic gist that we're going to have these now as restriction maps. This should be pretty familiar to you, right? We're going to have restriction maps down here to each of these intervals, right? Are you comfortable with that? This is our old friend, the restriction maps down from our intervals. And what's one of the things that's rather attractive about this framework is that these are going to be, oops, 4, that these are going to be C sets, the stalks are going to be C sets. Okay. So just without wanting to take too long on this, we're going to have that. And then we're going to have F13. And should have drawn that more artfully. And then we're going to have F14 here. Okay. Okay, poorly drawn, but you get the idea. Now, what's a key point here is that at this base level, there's going to be a certain type of logic. So these things here base ones are, in their words, snapshots. Of the situation at a given time. Mm-hmm. And they are C sets. So they can be variously mapped they can be associated with sets, in this case, sets of companies. They could be associated with graphs. If we had C sets with the graph schema, instances of the graph schema, right? Remember where we have E and V and source and target? These are instances of the graph schema down here. And they could be, gosh, they could be causal diagrams. They could be stock and flow diagrams. They could be stock and flow diagrams giving values for each stock and each flow. At a certain point in time. And what's notable is that this level here, this level one up from this, is not produced. So I'm going to go back to this. We're going to look for the data associated with so you'll notice that this structure here, this, let me put on one of these things. Hey, why aren't you? Okay. Let's go do this. This structure here, I'm going to make that this structure and this structure and this structure form these squares. And over here on the left, we have a thin category. And therefore, it is in the nature of things that all of these, all of these guys commute, right? If you go up like this and this, it's the same as going up like this and this, right? And this mapping here, because it honors compositions, like any functor, you're going to have this commuting, this commuting, this commuting. And you're going to have this. Oops, sorry. I did it at a wrong angle. All right, you're going to have these be, I shouldn't show it as, I need to draw it as a right angle. You know what I'm drawing? What are these things? They're pullbacks. They're pullbacks, right? So these ones here, these can be calculated as pullbacks based on the structure below them. You can do a pullback up, as it were. And you're basically characterizing here things that persist over time as time goes. You're characterizing things that persist across these intervals. And it's propagating broadly upwards here in terms of calculating what's present. At least that's how I think about it. Now, you have to recognize that really it's calculating relationships and just ensuring these relationships. But there's something more to the situation, and it's actually one of the reasons I started drawing this now from my slides. We talked about the Johnstone coverage here, condition. Cover of an interval is given by this. And there's a condition associated with persistence. In order for this to be a sheaf, it has to abide by a certain property. Okay. And you recall, so sheaves can be thought of as these functors that honor limits in their maps. It's not guaranteed that a functor always honors limits, but if it does, you can get these nice properties. And one of the ways that this comes out in sheaves here is when you have two intervals that overlap, if regardless of the particular subinterval here, let's take this guy up here. If the pullback going up to that guy this way, I'm not sure why it's this way, is with 3, 3 being the point in common. This would, I'm pointing here to, so we're having restriction maps. These are the restriction maps going down from this, right? We have restriction maps going down like this, right? We have restriction maps going down like that. Oops. Let's okay. If they have the same value down to PP either way around this square. So here it needs to give the same value here. This value, regardless actually of P. I'm not expressing it well, but regardless of P, we have to have the same value up here as well, as my recollection, and I'd have to go confirm that. But regardless of where we break things up, whether we're dealing with 1, 2, and then 2, 4, or whether we're dealing with 1, 3, and then 3, 4, we have to have the same value drawn up to here. And this is this condition that I'm recalling here. So let's see if I can find this condition, P comma P. Yeah, here we go. Okay, so let T be any time category associated with the Johnstone coverage. So here's our T. Johnstone coverage says if we have an interval, like say 1, 3, then we can form a cover of it if we have like 1 P and P the final one. So like 1, 2 and 2, 3. That would be the Johnstone coverage for 1, 3. So T is a time category equipped with that. D is a category of pullbacks. All C sets have pullbacks. So this is something like CATLAB, it's automatic because we have toe point. Then a D-valued sheaf on T is a pre-sheaf, so it's a mapping like this, satisfying the additional condition. For any interval AB, take 1, 4. Right? Any cover AP, BP, sorry, AP, PB of this interval. So our interval is AB, say 1, 4. Right? For any cover, 1, whatever 4, of this interval, f of AB, that particular value is the pullback of this. It's the pullback of this. So you have to have one value, you have to have a value assigned to this that is going to be invariant as to the kind of breaking point. So if you happen to break things up this way that I'm showed with the yellow, or you happen to break things up this way, where I go down like, so I'm talking 1, 4, this is breaking it up at 1, 3, right? And there should be also a 3, 4 here as well that can form the cover for that. Or if I break it up at 1, 2, 2, 4, right? If I go like 2, 4, regardless of the P, whether P is 2, as in this, or whether P is 3, as in this, the pullback on this whole pullback square, which is guaranteed to commute because this square commutes, and that one, this one, no. The pullback over this entire thing has to be the same. It has to be consistent with this. So whatever's going on, whatever you're sort of calculating, when you talk about persistence, it has to give the same picture, regardless of where you happen to break the interval up. If you're talking about something that persists, it's got to persist over all of it. So no matter where you break it up, that shouldn't matter for your ruling about persistence, right? So that's the picture here. Now, with co-sheaves, so this is the sheaf picture. And now I want to save this for co-sheaves, but how can I get my menu back? Where's my menu? Give me my menu. Hello. Okay. Okay. No, this no, that's that menu. How do I get my menu? You young people, how do I somehow extract a menu?
What happens if you push, I guess when you open Windows with it's gonna say push Alt. But I don't know if that's in virtual Linux.
I'm pressing Alt, but my menu disappeared. What do I how do I get back my menu? This is called Journal plus plus, if any of you can look it up. But this is like open. This is like new. I guess I could copy all these things. What I want to do is save as, really. Is there some way I can like summon my
Save icon is left beside the.
yes, but I save it. It doesn't do save as.
Dr. Osgood, if it is in full screen mode, the menu will disappear.
Okay, is it in full screen mode though?
No.
I don't think right. I think this is full screen toggle. Maybe if I toggle it and I then untoggle it. Okay, now
Yeah, maybe.
maybe this will, maybe it'll revive. There's my menu. Okay, thank you, Nastaran.
Welcome. Off and on again.
Yes, right. So when I was your folks' age, actually a little bit younger, we were putting into place the first, like they were designing for the first time these interfaces, right? With like menus and buttons and stuff like that. It was just like the formation of like, what should things do and how should these interact, etc. I remember when buttons like this came to the fore. Okay, so what's the difference with a co-sheaf? What's the difference with a co-sheaf? Well, with a co-sheaf, what you're going to have is you're going to have this disappear, right? It's no longer T up, it's T. And what's the picture like over here? Anyone? The arrow's reverse direction. So let's see if I can do this without butchering it. Okay, now I've got a nice little. So these.
Copy it and then. It's not necessary.
You can select the left part. To have a select square that we can only select the left part on the copy and paste.
You mean like to rotate it or something or?
No, like
Uh-huh.
you're manipulating.
Yeah, you're saying to like select an arrow.
No, yes.
I could select an arrow and try to flip it. The problem is the arrow head is often separate from the arrow itself, and it gets kind of painful. Take it from an old man. So I'll draw it this way. So this way we're gonna have arrows going up, right? These arrows are gonna go in the same direction as the ones in the left, right? Okay. Like this, right? And now, what are these going to be? What are these things going to be up here? They're going to be pushouts. Is it going to be pushouts? No, this is going to probably do terrible things. Well, okay, maybe it's not so terrible. Ah, okay. My design worked. Okay. Okay. So now we're going to have pushouts. So these guys will be, instead of pullbacks, these would be pushouts. So before, as pullbacks, I should have said, like when we had pullbacks, I'm going to go back to that for a second just to make the point. So this is going to be, in fact, I'm going to call this sheaves just into sheaf data, sure, stocks, right? So these ones are pullbacks. And you recall that the idea with pullbacks is that it's not that this is the product of these, it's the pullback of them. So what it's going to require is that it's going to, remember with a pullback compared to a product, remember a pullback for shirts and pants, it's shirts and pants of the same color. It requires them to match. And here, this and this need to match in what they depict for this, right? And in fact, what they depict for this, right? Like these two need to give the same picture regardless of where we break our P up. 1P, P4, regardless of whether we break it up at 2 or 3. It needs to give the same value between these two, matching values, just like matching pairs of shirts and pants, right? They have to restrict to the common things here. So that's the pullback picture, right? Needs to be same regardless of P in 1P P, this is the Johnstone coverage idea, P4, right? Regardless of where we break it up. And it needs these things to give consistent pictures. So it's putting together pictures of what's going over these 1 to 3 and 2 to 4 that agree on their common overlaps, including 2, 3, but including 2, 2 and 3, 3, etc. So these need to agree. So these and their restrictions need to agree, right? They need to be the same over the overlapping areas on overlaps, right? On overlaps. It's not just any product of these possibilities. It's ones that play nicely together, that are matching. Okay, now let's go back to our co-sheaves. What's going on here? Well, once again, these are like what's depicted here is not just it's not just whatever is in here, disjoint union with whatever is in here. It's not just those things side by side, because after all, they have some overlap. It's gluing them together. It's gluing the common areas together. It's gluing the overlaps together. You know, here, we are not just taking coproducts of these side by side, but gluing them over common overlap, right? Overlapping area. But you have this sense with push-out's like a variant of coproduct, right? It's like it's putting more and more things together. It's accumulating. It's with push-out, you're taking this alongside that, alongside that, alongside that. But to the degree that they are overlapped, you only take one of them, right? It's like union, like a union of sets. You don't, if you two sets overlap, set A and set B, if they have a common area, the union is going to be this entire area. It's not going to double count this, right? And so it is here. So here, we have this sort of building up in a cumulative measure of what's going on here, but take into account that there are overlaps. Okay, now let's think though about what's going on at this bottom level to go through this a little bit more. You'll notice, and I think what I'll do here is we will go take this data. So this is just the bottom two levels, right? Of it, of in the paper. This is the bottom two levels of this sort of lattice. And these levels are kind of special. Okay, so I'm going to be, I'll get these some bottom levels of lattice of data category lattice. So let's talk about this. So this is not created by some sort of pullback of this and this. No. There's no pullback square, right? There's no pullback square, right? So what's going on here? Well, what's going on is rather nice. Does anyone know the categorical name for this structure? What do we call it? It's a span. Do you remember that? Do you remember, like, if we have this, it's called what? A cospan, right? No. But what we have is a span here. Now, I want to talk about this span. This span serves a very important purpose. And it's important to understand it as such, because it's treated separately. Like, this is not calculated. This is actually imposed by the folks who designed the sheet, or that's told to the whole sheet frame. And I want to talk about it. Okay. It's a very nice idea, and it's one that some of you have seen, but some haven't. So in category theory, we have these various gadgets. You know, products and co-products and push-outs and pullbacks and exponential objects, equalizers, co-equalizers, monos and epis and so on. With this whole toolbox. And they're very useful. They come with intuitions. They come with affordances. They come with power and utility. And spans are no exception. So I'd like to motivate this. You'll notice here, these are sets. Do you see that? These are sets. They're not always sets. I mean, we should look, because in other cases, they can be from different C-sets. This could be a causal loop diagram that applies at different periods of time, intervals of time. But let's talk about them as sets. So when we have a set, I'm going to create a set A, B, C. Yeah. And I'm going to create a set 1, 2. Yeah. And I'm going to have a set up here that is going to not even tempted to not even give them a name. It'll be like the horse with no name. There it is. Okay. Jeff got that one. So did Larissa. Okay. So here we have our a set with 3 elements, and I'm not even going to name it. Okay. Now, if we had this be mono, this were a monic map. And we had an equal number of elements here that we have here. What would this be specifying? So each of these is, if these are sets, these are functions, right? These are functions. So, and the problem is I'm going to, maybe I will give these with apologies to the horse. I'm just going to call these Z here, X, Y, Z. Okay. So I can write down their names, even if the horse didn't benefit from that. Okay. So we're going to have X to 1, Y to 2. This is my notation for functions, right? And if this is mono, basically these things are just other names for these things, right? Mono means it's injective, right? You can't have X mapped to A and Y mapped to B to A also. It's just, right? It's like X might be a name for A, Y might be a name for B, Z for C, or maybe X is a name for C, Y is a name for A. But one way or the other, these are just different names for those, right? potato, potato, tomato, tomato, right? Right? Okay. So if this is mono, what are we specifying here? Like, what does this thing specify? It actually specifies something we're very familiar with. If this is, excuse me. Oh gosh, I did something stupid. This is going to be actually an isomorphism. I'm going to say this is an iso. So this is one-to-one basis. Mono just means it's a subset. Forget what it is. But this is an iso. If this is an iso, it's a isomorphism and it's mono in both directions. If it's an iso, what do I specify here? What is this thing? Well, it's a function. It's a function from A to something here, B to something here, C to something here. After all, we map Z, we have to map Z to 1. Okay. So this would be specifying a function from each of those to each of these. Right? Okay. Now, what if instead of being an iso, what if this is instead just mono? Just mono. What am I specifying then? So maybe I don't even have to have Z here. Right? I could get rid of Z here. Mm-hmm. What would it be then? Maybe I'll just to preserve that case so we can see it later. I'm going to put it. So if that's iso, I'm telling we're specifying a function. Okay, I'm going to say specifies function. Here we go. Specifies function. Each of these ones corresponds to one of these. And this mapping from this to this for each of these specifies some mapping here. We good with that when this is iso? Okay. Now let's copy this, and I'm going to make it just monic. It's not going to be an iso anymore. It's going to be monic. What is it going to specify then? What is it? If it's just a monic map, it's not iso. What is it going to specify? Hey. It's going to specify something very meaningful. What is it going to be? It has a special name. Okay. What is it going to be? If this is merely monic, I'm going to make it very clearly monic here. What is it going to specify? I will here, just to make it clear example, I'm going to get rid of Z here. Now this can be it can just be a subset, as it were, right? It can just specify a subset. Maybe X maps to A and Y maps to C, right? So what is it specifying then? What would this span be specifying?
Or say index.
Well, this is an injection here. So what does it specify? It's actually not a function. It's a what function? Begins with a P. Partial function. This is merely monoid. Specifies a partial function. Because it specifies, well, whatever maps X maps to over here, maybe X maps to A, right? Maybe X maps to A, maybe Y maps to C. This is specifying a partial function from ABC to 1, 2. So A maps to 1 and C maps to 2. Why do I say that? Because X corresponds to A. X is mapped to 1 here. Y corresponds to C. I should make this more clear. Y corresponds to C here. And Y here corresponds to D. So this is a mapping from A to 1, C to 2, and B maps to nothing. That's why you call it a partial function. Sometimes we write B maps to bottom, meaning it doesn't map to anything. It specifies a partial. Now, but in general, if I don't have a mono, so in this paper, there's no indication that it's mono. There's no indication that it's mono. I'm going to have X and Y. What does this specify? Well, let me ask, could you with this, could you specify a mapping? You tell me. How would I specify a mapping of A to A goes to 2, A maps to 2, B maps to 1, and C maps to 2? How would I do that? Okay, so if I want the net effect I want is A maps to 1. Did I say 2? Okay, I think I said 2. 2. So A maps to 2. B maps to 1. And C maps to 2. What could I specify here? What would these functions along this? If I want to get this thing,
Go to A and C.
sorry?
Go to A and C.
X goes to A and C. That's right. So wait a minute. So X, no, it has to go to 1, right? So what could I? Okay, so yeah, you got the right idea though. Okay, so what do we have to do here? We need A to go to 2 and C to go to 2. And Jeff had the right idea that if we add like X goes to 2 here, all we need is that like, yeah, so if we okay, so this actually we're going to need a Z. We're going to need a Z, right? That's what we're going to need. So we're going to need X, Y, and Z. I'm pretty sure. So X goes to 2, Y goes to 1, and Z goes to 2. We could get that by having X go to A. We could have Y go to B, Z go to C, right? These have to be functions. The net result of that is a function. But what else could I do here? If I have this situation, what else could I do? That I'm going to claim that no longer am I limited to functions here. This was a function when I had an ISO here. This was allowed me to do partial. Could I do a partial function here? Suppose I wanted B to not map to anything. Could I do that with this one? The answer is yeah. If I don't want B to map to anything, I could map, for example, so maybe I want A to map to 2, C to 2, and B to nothing. I could map X onto A, and X maps to 2. I could map Z onto C, and that maps to 2. I could map Y maps to A, and Y over here maps to 2, for example. That would be fine. That'd be fine. And so I could, in fact, have this. I kind of have unnecessary number of elements. But what I'm going to tell you is this actually can allow us to express a relation. A relation here. So let's try this. Suppose I wanted to have a relation between, so I want A to map to 1 and 2. So A maps to 1. So you may recall a relation would be like having a table where I have A, B, C on the one hand, A, B, C, and I have 1, 2 on the other. And it's like I have a check mark for those that I want to have. Okay, so if I wanted this, how would I do it? Well, if I want this relation, I could do it quite nicely. Clean this up a bit. What would I need to do? Well, I'll have X, Y, Z, W. Maybe I'll have V, W, X, Y, Z. Notice I'm picking 5 to map the 5 things here. Maybe I don't need all of those. But the idea would be that for maybe V is the name for this guy here. So I'll have V mapped to what on the left? On this one, what does it map to? Yeah, exactly. So I'll have V to A over here, and I'll have V to 1 over here. Now, suppose I want to have W capture this one. What would I map to? W to, on the left, what does it map to? B. And what on the right? To 1. Now, suppose I want to map to, I want to do this one. What do I map to for X? If I want to capture this one. Okay, X to B and X to what? Yeah. X, so F. Okay. So this was also to 1. X to 2 here, X to B here, because I'm capturing B and 2, right? And then I think you get the idea. How do I do the final 2?
I map 1 and C, Z map 2.
Yeah. Okay. Y is going to map to C over here. Y maps to 1 over here. Z maps to what? C over here. Y maps to 2 over here. Sorry, Z substitute, sorry. Yeah, yeah. So spans can encode relations. They can also encode, I mean, a partial function is a relation. A function can be expressed as a relation. We talk about the graph of a function being its relation. So they can express functions, but but spans give us, so again, a span which has a mono left can characterize partial functions. A span that has an iso left can specify isomorphisms. A span with no restrictions like that can specify relations. So what we're specifying up here is relations. These are two different relations. And the fact that we're specifying relations allows us to not just have things mapped one-to-one. Maybe I'll use a different color for good measure. Not just mapped one-to-one, but we can have some things which are going to not be found on the right, like B here. And so we don't have anything up here that has to map it. And now, if we want A1 and A2 over here on the left to merge, to be smushed together, what do we have to do here? What would we map them to up here? So if maybe what I'll do is just to use color to better effect. I'm going to go back to this and I'm going to specify A2 in a nice green color. Okay, so what do A1 and A2 map to over here? If we want the effect to be that they merge into A star, what do they map to? So companies A1 and A2 on the left turn into company A star on the right. What do we need to map A1 to on the right? This is a function. What is the mapping for A1? It's to A star. What's the mapping for A2? A star as well. What's the mapping for C? Well, C, right? So maybe I will just think, yeah, I'm gonna draw this a little bit better here. And then we have blue for this one. And then we have, for C, we have red. And that maps down to that. B, the interesting thing is here, we are not, like I would have thought we would have a B here. B would map to B over here and then B prime here. But I think the idea is B and B prime are different. What's that?
So you could means they don't have any relation.
Right. Right.
It's not necessary to be a function.
Yeah, that's
It
right.
even has to be mapped or.
Right. It doesn't need to be. Yeah.
We just ignore them.
Right.
No relation.
Right. And similarly here, like on the right-hand side, A star here goes to A star, B prime goes down to B prime. There's similarly no mapping of C over. And then once again, A star goes here. And B prime goes. So I should have drawn that underneath. Here we go. And B prime goes over here. So this level of mapping is ensuring, and this is a theme in the paper. I mean, one of the elements of philosophy that I got from this paper, which I found really interesting, speaking with my data science hat on, is that they argue essentially that at least what I took away from it is that for too many phenomena in the world, when we have data from one time point and from another, we treat them in isolation. And one of their arguments here was, one of the aspects that they tried to advocate for was the importance of relating data from one time point to another, of capturing that there are morphisms between data. And this is very much a categorical standpoint, right? It's not the objects that should be the focus of your attention. It's the morphisms between them. It's the relationship between what's going on, over here and what's going on here. That's just as important as what's going on at any one time. And they argue that we want to take seriously and empower analyses that will allow us to reason about these mappings here, right? These mappings, and compose them, etc., and reason about them. And with that perspective, which is, I think, really valuable for our group. I mean, we have this longitudinal perspective. If you think about these things coming out of dynamical systems at different points, there's some sort of mapping that's going on here over time, right? So this lower layer, which they specify to the system, is specifying these mappings. It's easy to miss it and think, oh, this is just the first layer of the lattice. But really what we are specifying here is a mapping. But it's not necessarily a function, right? It's not necessarily a partial function, although it has elements of partial, like B is not mapped. It's actually more general and allows a relation. And the fact that it allows this relation is really valuable, because it allows us to do things like merge two things here into a single thing here, right? It allows us to specify that some things persist here, like C persists over to here. Some things merge, and some new things some things disappear, like B disappears here, and some things appear here. B prime appear here. So they make the argument that specifying these mappings is important from a data science perspective. And I personally agree. I personally agree that you can get a lot more insight if you have data in a graph, from time one. And then you have data in a graph from time 2, like if all you have is this data in a graph, that tells you something. But often the more interesting thing is knowing, for example, is this person the same as that one? Is that one the same as that one? And knowing, is it that this person here has ceased connecting with this one, or is this a new person, etc. So their argument is you really care about those mappings, and these tools of Sheaves are a way to take advantage of those mappings. Now, one of the further advantages, though, that we have here from their approach and from this idea of using relations, etc., is that we can also specify data beyond sets. So we did it with sets there. Here we can say, okay, so this is dealing with, here they're dealing with fiber products of sets, right? They're dealing with, in other words, they're dealing with pullbacks of sets here. They're observing the fact that if this is a mapping here and this is mapping here with a function, you can pull this back and get the fact that basically we have persistence of A1 and A2 in their relationship with A star. They persisted. They happen to have merged, but they persisted over this entire interval. And they both, they were depicted as A1 and A2, but also they shared being A star here. This, by contrast, is a picture that could be generated from a C set using graphs, right? And okay, I don't know if I did something bad there, but here we go. So you're familiar, of course, with our classic schema for graphs, where we have and instances of this will be graphs, right? So these are all, these are all graphs, right? These are all instances of this schema, right? An instance of this schema, C set, right, can give us one of these graphs, right? Like this one here. So this is like a C set, right? Right? Any one of these graphs can be a C set. Okay. What are these morphisms? What are these morphisms that join it? What is this? What is this? Well, if these are graphs, what are those morphisms? Yeah, those are graphomorphisms. Those are mappings between C sets, right? Those are those are mapping between C sets, right? So this is you could think of it as a graph homomorphism, right? You could think of it as a natural transformation, if you want. I think a graph homomorphism gives a nice idea of like you can collapse certain vertices into other vertices, right? Remember, you can embed one graph in another, right? That's there's a natural transformation between, you know, and I can't remember what different, but like a graph said, so if this is GRPH, then these are graph sets, right? In CATLAB, there'd be AC set transformations. But these spans are now characterizing, as it were, relations among these graphs, right? And this is really interesting because now, as you see, A1, and I'm not going to, do all the sort of listing of the graph homomorphism, but you notice the net effect here, right? The net effect is like A1 goes to A star. A2 I don't remember what color I used for which, but A2 goes, it's the least bad way to do it. A2 goes to A star. C goes to shining C. Right? And B disappears. And B prime appears. So, oops. Sorry. So the point is, like, specifying things with these spans is not a hack. It actually allows us. Okay. Where's my C to shining C? Where is it? There it is. Okay. It allows us to specify these mappings in ways that are powerfully general. These mappings, even when we have C sets, moving beyond graphs, up above we had graphs, right? Up above we had sets. This is with graphs. And I'll just to complete the thought, I will draw B prime to B prime here, and I'll draw A star to A star here, and C disappears and C prime. And you'll notice that this mapping, it's actually specified itself as a graph, because in the category graphs, actually graph homomorphisms are graphs. In fact, I don't know if this will freak you out, but it's pretty neat. So graphs are C sets, and C sets build topoi, where you can do, which have exponential objects, meaning for any mapping, any set of mappings from one graph to another, there is a graph that describes that mapping.
Mm-hmm.
It turns out there's also a thing called the subobject classifier that specifies true and false for graphs. And there's a graph that represents true. And there's a graph that represents false, which is pretty neat. Anyway, so this is a graph that specifies this mapping here. And what we can do with these being C sets by using these spans is we can map them. We could specify these mappings between different time points, right? Because these are here different, right? These are specific time points, right? These are like particular snapshots. At single points in time, right? Time 1, 1, time 2, 2, time 3, 3, right? So this might be like time 1, 1. Maybe I'll put it right here. 1, 1, time 2, 2, time 2, 3. Sorry, 3, 3. Butchered that. Go. And oops. This is specifying, well, this together with its, its legs, right, and feet are specifying the mapping, right? I don't even know what color to do this in. Nice to do a nice bright color, but this is specifying a big mapping, but not a function, but a relation from this to this and this. That's what these are capturing, right? They are graphs, but they're capturing it. And with C-sets, you can do that because they have exponential objects. They have eternal Homs. For whom that might seem really odd, I'll just note it. In functional programming languages, if I don't know if you remember the category Hask. Do you remember what the objects are of Hask? They are types, sets of a certain type. So there's an object for like int, right? That's associated with all possible values of x. It's an object for a bool. That's associated with all possible values of bools, true and false, right? And what's an exponential object in there between int and bool? Well, it's of type int to bool. It's type of a function from int to bool is its type. And it carries as values all possible functions going from ints to bools. So Hask is a language which has internal Homs. There is a type that describes the mapping between any two types. And the values of that type, describing the mapping between ints and bools, say, are the functions from ints to bools. So it's nothing too weird that, like, there's a graph that describes graph homomorphisms. But that's what, these mappings, right, that are characterized. That's what's at that level. And so when we go back to our category here, just remember that what's going on down at this level are these snapshots. And what's going on is that we are specifying mappings between them. And I believe that, excuse me, those are over here. Really, I should be saying these. These are sort of mappings between. And I believe that those are basically captured here. I believe we are specifying this level as the mappings here between these points. And then the rest we can compute. These things and I'm not sure how to do this non-obnoxiously. These things are computed. So I think my reading of it is that, and I did ask I think Matt Cafaro, maybe Ben Bumpus was on the call as well. These are like given. Right, like these ones down here. Given from snapshots. This, I was going to put that in the same thing here, but I think I'm going to put it up here. This is given by mapping between snapshots. So in other words, like we bring that to the table. We specify that mapping. Like we might specify, oh, this graph here with these things here at time 1, in this graph here, these mappings at time 2 with this graph, that we specify, oh, this person is the same as that person is the same as that person, is the idea, I think. At least that's how they're sort of suggesting it be done. And then these items up here are computed by virtue of sheaf properties, or by virtue of the sheaf constraints. And we can kind of run the sheaf machinery and get out cumulative things against, across, or this would be persistent things. And these persistent things like will be in the appropriate data, right? Like, so in other words, for this guy here, what we will be getting out at those upper levels the sheaf is giving it are sets of things that persist across all those time periods, right? What we would get for this one, right? Remember, it's like pull back. It has to be present at this time and this time and this time. It has to be present at all constrictions to different points in time for it to be there in the pull. Remember the pullback of sets? Do you remember what a pullback of 2 sets is? It's the what between the sets? Intersection. And so we are intersecting up, right? That's what's going on here. We're sort of intersecting up, like with those sets, which guys are still around, even if they change names, even if they merge, which guys have stuck around. Maybe they were A1, A2, but now they're A star, but they stuck around and they'd make their way up to the top, the tippy top. Intersection, but taking into account different fact that some merged, right? Some split, and we might take into account that some, like, remember relation, right? Like one thing could go to 2 different things, and the next it can go, A could split into A1 and A2 in the next one, right? But with co-sheaves, well, let's go on in. With co-sheaves would be accumulating up, right? Would be like which things over any time period were present. There was a B prime at this time. Back then, there was a B double prime. This other time, there was a Z for a while. And we could be accumulating up. Remember, the idea is like push out, keep on accumulating things, take into account that if there's overlap, we merge them, we glue them, whatever. Yes, Mehdi. Yeah.
You have dynamic and different snapshots.
Yes.
But I'm running dynamics, things like that.
Yeah.
Situation that the dynamics of the system change over time. If you have a dynamics in a snapshot, but we know the relations between the between the, for example, the state variables.
Yeah.
Different snapshots. If you know the relation, you can find the consistent dynamic in here.
Right. I think that's right. That's right. So you might find some elements of the dynamic that are preserved over all time points, even though certain elements change in for different points. You could also find through the cumulative perspective elements of the dynamics that were there at any point, for example, right? Like maybe certain flows appeared only for certain periods of time, and you'd be able to capture that. It probably bears note, and then we have to finish here, that if we're dealing with graphs, if that's our CSAT, we're dealing with graphs, then up here will be a graph, right? That will be the persistent graph, the graph and its nodes and its persistent connections that persisted throughout. Capture connections that have to be here. No matter where we break it up, they have to be present. And if we had a code sheaf, it'll be the graph up here will be accumulating the people, the vertices. Take into account that we won't double count, like if it was merged or whatever. But I think like vertices and edges that were there at any point. So maybe you had people, these two, B and C, A2 and C work together here. A star, the A1 and A2 merged into A star, but they stopped working with C. The cumulative perspective would include the link from A star to C, I think, because it existed at any point. Push out sort of glomming things together that existed at any point, puts them side by side. So you would have a link between those two, even though it was now gone for some of the time. You would have up at these top levels, like an elephant, it will remember. It'll just accumulate this up to the top level, right? Okay. That's all we have time for today. I have to get back to my office for a meeting, but we're going to continue on this paper next time. We're just partway through. But I think you're getting a lot of the core ideas here of it. And we've talked some about things like change of base functions and the adjunction and other components on Friday. We good?